We're going to take an ellipse that's currently in general form, remember that's the unhelpful kind, and transform it into standard form so that we'd be able to sketch the graph. To know how to sketch this, we would like to know the center and then of course the denominator of the x squared term and the denominator of the y squared term. This is going to be a little bit more messy than doing, say, a circle, but we can certainly accomplish what we need to accomplish. So we're going to start very similar to the circle. We're going to group our x terms. We're going to group our y terms. This should look familiar. And we're going to move our constant to the other side. Now in the circle, when the lead coefficient wasn't 1, we could just divide everything by that value because it was the same for the x and the y. That's not true for the ellipse. You're going to have different coefficients on your squared terms, so we're going to have to kind of treat them individually. So we turn our attention to the x's. We need this to have a coefficient of 1 instead of 25, so we will factor out a 25. 25 times what gives me 150x? That's going to be 6x. Now for the y's. We have a 4, so we take out a 4. It's just pleasant that it's a common factor. It does not have to be a common factor. 4 times what would give me negative 16y, negative 4y. And then there is our negative 141. So we complete the square. Half of 6 is 3. 3 squared is 9. So I am adding 9 inside this binomial, or this trinomial now. And what we have to remember though is that 25 is multiplying that 9. So what we really did was we added 9 times 25, which is 225. So I need to add 225 to the right hand side. Similarly, when we take half of 4, we get 2, and 2 squared is 4. So I'm going to add 4 inside the parentheses. However, that 4 is getting multiplied by the 4 on the outside of the parentheses. So we didn't really just add 4, we added 4 times 4, which is 16. We now factor our trinomials, and we have 25 times x plus 3, quantity squared, plus 4 times y minus 2, quantity squared, is equal to negative 141 plus 225 plus 16. So that is, let's see, 241 minus 141 is 100. Then the last part for the ellipse is get your equation to be equal to 1. That was not part of the circle. This is part of the ellipse form. So we want to divide by 100. Well, that means we divide by 100 on both sides to keep the equation balanced. 25 goes into 100 4 times. So we have x plus 3 quantity squared divided by 4. 4 goes into 100 25 times, and that leaves us with y minus 2 quantity squared. And of course 100 divided by 100 is 1. Now this is standard form. We're able to look at this and identify the center of the ellipse to be negative 3, 2, and we will plot that location, negative 1, 2, 3, up 2. There's my center. From the center, I will go out in the x direction, the square root of 4, which is 2, left 2, right 2. And in the denominator of the y term, I have a 25. Square root of 25 is 5. Y reminds me of the y-axis going up and down. I will go from the center up 1, 2, 3, 4, 5, down 1, 2, 3, 4, 5. And I am able to sketch in my ellipse. Now let's talk about some terms associated with an ellipse and actually define an ellipse. We've been graphing it, transforming it, but let's see a little bit more precise definition. So the definition of an ellipse is the set of all points P in the plane, the sum of whose distances from two fixed points called the foci is a constant. So let's pause right there. So we're going to hit the brakes. Looking at this picture, I think you'll get a good idea for what's going on. We've got these 2 points inside the ellipse called the foci, and they're going to be equidistant from the center. So that means the same distance from the center. If you pick any point on the ellipse and you add up the distance to each foci, each focus I should say, whatever that is equal to, if I shift P to here and I find this distance and I add it to that distance, you get the same thing every time. So the distance from those 2 fixed points, the sum, is always going to be constant. The line segment that contains the foci is called the major axis. So in this case, here is going to be your major axis. It has endpoints on the ellipse and it passes through the center and the foci. It's also the longer of the 2 axes, which makes sense as it's called the major axis. Then the minor axis is through the center perpendicular to the major axis, and it's going to be the shorter distance. So if we look back at our ellipse here, we can see that it's longer in the y direction. So here would be our major axis. The green would be the major axis. And the shorter distance is here. The orange would be the minor axis. All right, a tiny bit more terminology. So when you have an ellipse that is kind of flattened out, you're going to have a horizontal major axis. When you have a taller ellipse, you're going to have a vertical major axis. So I encourage you to read through this. All right, let's turn our attention back to this picture. I'm sorry I went past it before spelling this out. How do we find the distance from the center to the foci? Well, as you see, I've got some little C's in here, and that doesn't stand for center. C is the distance from the center to the foci. And C squared is equal to A squared minus B squared. Now, what I'm about to tell you is going to be a little bit confusing, but bear with me for just a minute. When we introduced the standard form of the equation of an ellipse, the way I presented it to you was that A squared was under X squared and Y squared was under B squared. Depending on which book you look at, that's not always true, and that includes our book. It's not always true that A is under X and B is under Y. The way this book describes it is A squared is always the larger and B squared is always the smaller. So, how are we going to wrap our mind around all of this? Well, here's what I would encourage you to do as far as where this is going to be useful is finding the foci, the distance to the from the center to each of the foci. This is always going to be the larger denominator minus the smaller denominator. I would prefer you not even think in terms of A and B. Just think of the larger denominator minus the smaller denominator. And that way you can remember what we have already learned. So, if that's not too confusing, let's see if we can come back here for just a second. So, here's where we found our equation of our ellipse in standard form. Let's say we wanted to locate the foci in this ellipse. Well, the distance, C squared, is equal to the larger denominator minus the smaller denominator. So c squared is equal to 21. C is equal to the square root of 21, which is about 4.5-ish. Okay. So the foci are always going to be in the direction of the lengthier axis, of the major axis. So since the major axis is vertical here, from the center we will go up 1, 2, 3, 4, and a little bit more. Down 1, 2, 3, 4, and a little bit more. So these foci are very close to the edge of the ellipse, but they will always be on the inside. If we actually wanted to locate where they are, we usually want to do that in an exact form, so we're going to want to use the square root of 21. Our center is -3, 2. So you ask yourself, which part of the center got adjusted? Did we move right and left? If so, the x got adjusted. Did we move up and down? If so, the y got adjusted. Well, we moved up and down. So we're going to add this to the y part of our center. So -3, 2, plus and minus, because we went up and down, the square root of 21. That's the location of the foci.